in the in YouTube. Probably I missed to upload it just a little wrong, but I will upload it. Yeah.
Thank you very, very much.
All right, so what we went through yesterday, we talked about how lensing distorts images and surface brightness, and that we can define them in a relatively simple equations of the mapping of where we see something on the sky. We deflect it back of where it originally came from, and evaluate the surface brightness or in these original coordinates where they came from, and they correspond then to, when we introduce that mapping, is then the lensing distortion. In the linear regime, we can do a linear distortion matrix, the lensing Jacobian, where we can write this mapping between where something came from, or the relative angles of an intrinsic source to the relative angles that we see on the sky. We can also do the inverse of it. So when we know a shape in the actual source, how the shape looks like when it's being lensed. And this is a typo of being -1 effectively. Yeah, which I'm going to correct next time. And so we then introduced or described this shear and convergence terms, how they can be defined. And in particular here, there are in terms of an axis, so of the first component of the vector and the second component of the vector, where in that case, I defined it as the x-axis and y-axis, or that's how I plot these two components. So shear 1 is along the x-axis and shear 2 is off diagonal to it. And then we talked about how a spherical source can be lensed. Oops, run away. And we saw and experimented with, when depending on what intrinsic shape we put in, when we distorted with shear and convergence, how they look on the sky as well. And then we can generalize this notion of when we don't know what intrinsic shape is and what the lensing is with shape noise, so to speak. And so there's some math that makes a correspondence of operators of when you actually see something, or when you don't know what the intrinsic source is, there's a correspondence of changing effectively the ellipticity or the shape of the source, while simultaneously inversely changing the lensing effect. And then the last part was then when we have multiple images, and that's the strong lensing regime, where really the advantage comes that we have multiple images that we see on the sky, and we can learn about the relative distortions between the multiple images. And that's this part here, and that's an observable regardless of whether the intrinsic source looks like S or S tilde in that component. So that's a general way of defining lensing degeneracies of what we can see when we don't know the source. And the specific one is the mass sheet degeneracy that has a certain physical correspondence that, or we can define an interpretation physically what it means. And we experimented here in this box by setting up a source that's being lensed, and it happened in that configuration have like 4 extended images, and we can do different transform. They look identical in the image plane, but the lens itself, the lens model is a different one. And so you see the inner caustic being shrunk or larger, while the image positions and all the relative observables remain in value. And so the summary of that part is that gravitational lensing observables multiple images the constraints are relative image positions, relative time delays, relative image distortion, and relative magnification. This is really the information we can extract. And only when adding external knowledge about, be it either the intrinsic size, shape, or brightness of an object, before it's being lensed, further information can be extracted. So that is the main part we walked through yesterday. Any questions so far? And then the next part we did yesterday was I put this notebook up.
Simon,
Modeling.
I'm
Yeah.
sorry, I don't know how to raise a hand here, but I have a question about the double lensing or the double image. For example, if you have multiple images, for example, this formalism can be taken to this.
Yes, so here it's just 2 images, but if you have 3 or 4 images, all these relative distortions can be measured, or to at least to the level the data allows us, yes. So you can generalize that in terms of, here in the text I have I and J, so it doesn't really matter whether it's 1 or 2, or have more images. So the more images, the better the constraints.
Because and this question is because in strong lensing, well, we have multiple images, and I thought that the strong lensing is kind of non-linear. So even if we have some multiple images, we can do this as many as we have. It is kind of a linear behavior, right? Isn't it like a superposition kind of?
In this framework here, in this formation, these operators do not need to be linear. So the distortion between S and S tilde, this is not needs to be linear. It's just, this is the linear is the easier one, and is the most like prominent in weak lensing, that this distortion happened mostly linearly. And so the exercise here was with linear distortion. If sources, even if they're multiple images and highly distorted, if you go very locally, at one scale, you can approximate it to be linear. But this may be a very small scale. And if you extend over a larger area, the non-linearities become more and more prominent, like curved arcs, while locally you may just see a tiny little eddies.
Great, thank you.
Any other?
One question. We have seen the case of multiple sources, but there is something similar for multiple objects that are in front of a source and cause the deflection of light.
Say again, what's your question?
There is a case similar from multiple sources that cause there is multiple objects in front of a source that cause the deflection of the light.
Yes, so that's effectively the transition to this notebook. Well, here I don't have it, but in the model that we do, and normally in reality, the lens that causes the distortion is actually has a galaxy in there. So in the center of the lens here, you can think of as like a massive elliptical galaxy or some galaxy. So this is the object that caused the lensing. And so we can also then state or assume, if you want to, that mass follows light to some degree, so that the center of the lens model, of the lensing, is actually aligned with the center where you see the light, for example. That's the assumption you can do if you want to, but you don't necessarily need to run with this assumption. You can see, probe, is there actually the mass, is it offset of the light? But in the modeling, it's in reality, we have this different light components, some being distorted, lensed from the back, coming from the background, and some are not really being lensed, just coming from the deflector itself. And so distinguishing these types of components can be technically difficult. Yeah.
Okay, thanks.
Any other comments so far? So in the next maybe 15 minutes, I recap and go through this Einstein ring notebook that I'm aware is not as much commented as a lecture note, but it's more like a go through in rather high speed through the different modules and to generate and model an image. So what's been done here is we mock up a distorted image that has the lensing as a source, a lensing effect, convoluted, pixelized, and has noise on top. And then we try to propose, or the model is going to propose a lot of models with different configuration as is the predicted model and the mock that we generated consistent with each other on the likelihood level, on the pixel level. And what you see here is the residual of the data minus the model divided by the uncertainty you give in individual pixels. And the question is, do we have the same result image if we change the order of operations? Good questions. The answer in theory is no. So that's basically how the order is of how photons move through the universe. And so these are not bijective in the sense that you need to first put in the lensing, then it's getting convolved, then it's pixelized, and then adding noise. So if you first convolve the intrinsic source and propagate this convolved image through the universe to do the lensing, that's a different operation. So that doesn't result in the same answer. And so the answer is strictly no. You need to follow these steps. You need to follow the paths of the photons. But yeah, good question. Yeah. So in the next part, this is really a very crash course of lens astronomy. I can also highlight, I think here I'm not sure I linked it now. I linked the lens astronomy starting guide notebook that goes a bit in more commented way into the different modules and what they actually do. And this here is less commented and meant to provide an end-to-end example of an Einstein brain. So what this notebook does is we first set up specifics of data. So this course does not, I don't have the time to go into astronomical data itself and how images look like, but generally speaking, or a bit simplified, have some background noise level that the data has. We expose for a certain time, in that case, just say like 500 seconds. And we cut it out 60 by 60 pixels. And for a Hubble Space Telescope, a pixel size in U is about 0.05 arc seconds, so very small pixels. This is a full width at maximum. So this is the kernel, the PSF kernel, so how much the image is blurred. Here, this is a little blurring. You can also experiment by adding more blurring. So this is basically that operator that goes from here to here, how much you blur the image. This is the next part. So the next part should be at least partially familiar. So we define here a lens model, here two components, a singular isothermal ellipse and shear. And these are the parameters that we say this is our input model. Then we have our lens model class. The second one is here we define a Sersic profile, where we say it has a half-light radius of 0.1 arc second, Sersic indices of 1, and some ellipticity here, so E1 and E2, and some position that is slightly off-centered. So, and we have a second light profile, which is the lens light, so the undistorted light from the deflector itself, which we set another Sersic profile with slightly larger extent of 0.6 arc seconds. Here we effectively use the IMSIM image model class, which effectively here packs together the lens model, the light model, and simulates images. And so we pack this configuration here together in the data object, which has all the information about the data or that the coordinate system, image properties, and so on. And so here, I need to execute this part before. This leads then to an image. And so here we illustrate it. So you can see this is the Einstein ring being blurred. You see the noise. And so you can also play around and say like, okay, what if I change the position of the source to be more off-centered? Do it again. And see how the image looks like. And you see barely any lensing anymore. You just see it on the side here. And then maybe here a secondary image that is barely detectable. So I move that back to a position where it's more like an Einstein ring. And again, and it should look about the same that I had. Modulo random noise has been changed. So the next part here is the model fitting. So here we need to define for the fitting, do you want to have some parameters just being held fixed that we either believe or we don't care and we just fix them? Here I decide I don't want to fix any parameter in the lens model. I give it an initial, what we need to do when we come fitting. This is general, that's not just for lensing, for any kind of fitting procedure that you apply. You need to have some guess with some spread of where you want to start. There's no fitting procedure that comes without that. Either somehow it's learning it, or you have to specifically provide it. And so here's an initial guess of the lens model parameters and initial uncertainty in these parameters. So you can play around with those, and depends on how broad or how offset you do the guess, the better or the worse the performance of your fitting actually results in. We also give bounds to the parameter. So we say, whatever the Einstein radius is, it must not be below 0.01 arc second. So definitely not negative Einstein radius. And we restrict it to not more than 10 arc seconds in that case. We just know it's going to be around 1 arc seconds or whatever. So this is for the SIE profile, the same for external shear. And so it goes through then the light components of the source, the light component of the lens, and puts them in a general keyword parameter. So that's all the configuration. That's this guy. Then the next one here, we define what we actually execute. We execute a particle swarm optimization of 200 particles and 200 iterations. So how it actually fits and finds the best fit, and followed by an MCMC Markov chain Monte Carlo. Here, burning of, so we disregard the first 200 sampling and then sample for 600. So it's very little sampling, and there's just primary made such that the notebook actually runs in a finite time for you to actually execute. But just it's an example of how this happens. And so while this is being run, here there are convenient functions to actually plot the results and to illustrate them. So this is the initial image that we had. Let's see the chat. Are we using flat priors? Correct. In that sampling here, there is no additional prior or there are flat in the parameterization we choose within the bounds that we're giving. You can put in additional, be it Gaussian or any custom priors in the parameters if you desire so. But here it's all flat in all the parameters. And so this is here the best fit result of that fitting. Here's the reconstruction, which doesn't have any noise. This is how the source that we reconstruct looks like. This is the convergence, so the density, the projected surface mass density, scaled surface mass density of the lensing, and here the magnification. And here we can also then split all the components. So here's the lens light of the model. Here's the lens light as it's been convolved, so slightly blurred. Here's the source light. Is the source light being convolved? And here all the components together. And all components with convolved is the same as our actual model that we compare to the data. Okay, it's going for about 5 minutes, so I'm not re-evaluating those. And so in the next part here, we see how the fitting procedure actually goes. Here's log likelihood, so minus log likelihood. So small numbers are better fits and a large number are worse fits. So the fitting starts pretty worse and then becomes better and better and better, and then starts kind of like plateauing to have a very similar goodness of fit. And here we see what the particle or the values of the fitting does. So it starts, you know, random or scatter. It doesn't really know. It goes, all the parameters walk somehow in a direction, and at the end they seem to be very stable. And this is the velocity, so how fast the particles actually move through the parameter space. So they start, gain a velocity, so they need to move in directions where they fit better, and then they start dwindling down, that they basically get not so much move. And this here is an illustration of how then the Monte Carlo Markov chain evolves, how the particles in the sampling of the MCMC chain evolves. The likelihood is rather constant, which is good. So if it would decline, it means it would go somewhere where it's better fit. And you see this kind of like oscillation patterns that the clouds is moving within the parameter space. And here are the parameters being plotted that's being sampled, which corresponds to posteriors. So I'm very aware this is like full speed going through a lot of concepts that you may or may not be familiar with. So there's a lot of like statistics, likelihood, sampling, and software. And so this is just, there are other resources when you go into, okay, how a particle swarm works, how statistics of a Markov chain Monte Carlo works, what are type of diagnostics, whether you should trust the results or not. And also starting notebook that introduces you more into the design pattern and what kind of options you can pick to run the modeling. And so this is just a crash course in kind of like what are the necessary ingredients to actually do such a modeling. Questions. So one thing you can try is, for example, you can change the input model and then ask yourself, okay, and do then the exercise again and see how well it actually can reproduce the mocked up data. Or you can change the signal to noise, so you can change the noise pattern and see then how it actually impacts constraints on parameters. So the more noise, the broader the constraints are, because there's less information it actually can use, and vice versa. Any questions in that regard for now, or otherwise when they come up, please let me know. So in the next part, so I stopped sharing here my browser and go into the slides, the first part of the slides. Which are also linked to the GitHub repo. And so I want to dive a bit more into dark matter inference and then go or point you at the last notebook with it. So just a short recap. This is the illustration that you saw. And in terms of a lensing perspective, what we're really interested in is how these distortions go. So what is actually the lensing effect? Is it granular? Is it smooth? How is it elliptical? Is it round, etc.? So that's what we care. And we have a lot of things that we need to know. So we need to know when we care about this effect, how is the convolutions? What is the properties of the data? So what is the signal to noise? What is the pixel size, etc. This is all things that we need to know sufficiently accurate and to learn about the lensing effect. So that's one comment. And the other is we need to deal with a lot of nuisance. Nuisance in that sense means a lot of degrees of freedoms that we're not targetedly interested in, but they may affect our outcome, so that we have to care. It's our duty to care in that sense and carry through. And you see that galaxies can be rich in their morphology. Here it's just a beautiful spiral that maybe some of you know its name of. When you Google galaxies on Google, you might find it. And so we have to marginalize our these uncertainties. And so in the next part, it was mentioned last time. So, okay, what about shapelets? What about pixels? How do you marginalize our complex morphology? And so and go a bit in detail here. So this slide is a bit technical, but it's applicable, I think, also to many other problems that you may or may not encounter through your scientific or scientific, engineering, or business career. So what happens here is we have a data that is very complex. So, for example, this beautiful Einstein ring with a quadruply lensed quasar. And you see here the spiral features here. You may play the game, where is the counter image of this guy? Is it this guy or is it this guy? And is this guy the same as this guy, etc. So you can play the game of where do these counter images come. And the idea here is to transform the complexity into a linear equation. So whenever possible, linearize your problem. And what can we linearize here? We can linearize the complexity in the source for a fixed lens model. So for example, we can define a basis function in the source plane that can be pixels, that can be Fourier modes, or in that case, shapelets, which are Hermite polynomial convolved with a Gaussian. So the idea is that a finite set of a basis function is sufficient to represent the complexity that we have in our data, and in our case, galaxies. We don't know how the individual galaxies look like, but we think we can capture the complexity with it. And we don't know how much each of these coefficients contribute to it. But what we can do is we can forward model all of these coefficients individually through the same lensing kernel, through the same convolution kernel, and also pixelizing it. And so we can represent this basis set in the source plane, an analog in the data frame, so in the image plane. And now what we can ask is, for that given lens model, what is the best linear combination of these data vectors, so to speak, that best mimic our data? And that is a linear problem. So we can solve a linear problem on this side. And we get coefficients for the basis we choose. And then if we want to evaluate the source, and to see what source corresponds, we can just evaluate the same thing on this side with the same coefficients. And so linear equations are super fast relative to solving nonlinear problems. And so whenever you can linearize parts of your problem, it can be beneficial. And it is here generally known, the entire fitting of lensing is known in that case as semi-linear inversion. So some parts are nonlinear, other parts are linear. And the more are linear, the faster, the more efficient it becomes. So I would like to show you some movies to illustrate that here. So what we have here, I mocked up an image here that has noise. That this is the simulated galaxy that I lensed through. And what you see here is the best reconstruction that the model finds if there is one single coefficient, a single Gaussian in the source. This is the polynomial order n max equals 0 in shapelets language. So that's the best. If we only have one coefficient, it solves the linear equation to effectively just fit the amplitude done. And you see image residual clearly doesn't fit. And the source also doesn't really look like the source that we put in. And now I run the movie, and what I do is I increase the flexibility or the number of basis sets that I allow to be fit linearly in the source plane. So nmax is the number of polynomial orders in the basis set. And we've increased nmax, the reconstruction is better and better able to actually describe the data and the source. And I run this movie here. And you see by now it starts fitting and describing spiral features. And it gets better and better and better the more complexity it includes. And it starts getting towards a perfect fit. And probably by now it even starts overfitting the data, that we actually put in too many degrees of freedom relative to the data. The reconstruction of the source is not perfect. There are multiple reasons for it. A primary one is there is a blurring operator, so the seeing, so we don't have really access to the full information. And so there's always some uncertainties in what the reconstruction and the actual source looks like. And some of the uncertainties are the wiggles are then specifically to the basis set we're choosing. So this is, here I, in that sense, cheated. I put in the perfect lens model. And so I expect the perfect results to some degree, though this linear set does not represent those guys. But I knew the lens model, so everything worked fine. The next one here is where I do not know the perfect lens model. In particular, when I mocked up this image here, I plugged in a small perturber, a dark perturber that distorts the lensing, which in my reconstruction, I do not put in. And now I ask, well, I don't really know. I clearly don't see whether there's a perturber here, or if you can tell me where this slight perturber is, raise your hand. And what I also don't know is, well, there may be a different source that can counteract this. So it can replace a different source morphology with such a perturber. And I run now this exercise and see what's happening. So at first, it does basically the same as before. It fits the macroscopic feature, it gets down the residual, gets the spiral feature. But by now you see that in the residual that something just remains that does not go down. No matter how many basis sets I add and complexity I throw on the problem, these residuals do not get down, while at the same time other regions get overfitted. And this is here a sign that A, we can actually extract small scale information from lensing. And the reason for it is that we see the same source, even though we don't know what the source actually looks like. We see it multiple times. And so we demand that it's actually the same source that leads to the relative distortion over here and over here. And what you see also in the residual, maybe of the guided eye, I mean, here you see a big blob of yellow residual, so I think it's not getting the right surface brightness. But you see also the opposite blue features on different parts of the ring. And that's where the other components of the same source actually needs to be fit. And so this relative distortion of how much why we can learn about small scale structure. It's challenging. It requires marginalizing over nuisances, but this is kind of like a proof of principle, so to speak, to extract information. Are there any questions so far? Otherwise, I quickly stop sharing here, move back to the slides, and in particular to the substructure notebook that you should also have linked, and I just shared it. So this notebook here, strong lensing with a substructure, a simple example, is basically the same as I run you through with an Einstein ring, where we have the perfect lens model. It's a singular isothermal ellipse with external shear. In this example here, that you can then also experiment if you're interested in, we added an additional little perturber in case in here as a Navarro-Franken-White profile. And we added it here as a rudder with a certain mass and concentration relation to it. And so in this example, that's how the lens looks like. And the perturber is somewhere over here, a tiny perturber. And this is the image that we produced. And then in the next blocks, we do the same fitting as before, but only with the smooth model. So we don't add here the NFW component in it. Ask, can a smooth model actually fit the data? And these blocks are basically identical, except that I here put in an elliptical power law profile. So I allow the power law profile to vary as well. So same parts, basically identical command. The only thing, I only run here the particle swarm optimization, but you can also run the MCMC. And what comes out, depending on what you plugged in, is something that, well, by eye fits very well, but depends on the noise property. You see some correlated residual patterns appearing in when you compare the observation that has a clump in there, and that is somewhere here, and without, and you see residual patterns appearing. And that's an exercise you can do, and you can also see that. And I laid out here some exercises that you can do to gain more intuition of it. For example, you can increase, decrease the signal to noise, increase and decrease the resolution of the point spread function, and change the pixel scale. So this is the observation. So if you change the quality of the observation, you will get, for the same substructure, more or less prominent residual patterns occurring in your fit. That's one aspect. And the other is, you can also experiment with where you put the position of that additional clump. And when you change the mass of the clump, or the concentrations, how concentrated the mass is of the clump, and see how this is impacts whether and to what degree you can find it, or it results to a residual pattern. And that's basically that notebook here. I don't I don't execute it in that case, but you have here the resources if you're particularly interested in that problem example. So some of the problems are rather highly simplified. For example, the source here is just a surcic and not with hundreds of shapelets basis sets on top. Primary for computational reasons that you can run that in a few minutes through. And pedagogically, the ideas behind should be similar in qualitatively what you expect to see when you vary different parameters. Are there any questions to this?
Yeah, well, I have one kind of silly, but do we have any proof to get noticed when we got to overfit it?
And that's a great question. And so there are, for example, so the easiest and a bit crude statistics is the so-called chi-square, or the reduced chi-square. This is the difference between, or the how on average residuals on each pixels are. So are they 1 sigma off, 2 sigma off by the data, or 0.1 sigma off? So the square of that difference, the sum of this divided by the number of degrees of freedom, or by the, yeah. And so what we expect is that effectively per each of the data points on average is randomly off by 1 sigma relative to the measurement. And that basically means that it describes statistically the measurement. So random noise at 1 sigma is exactly the description what the uncertainty means. And so a reduced chi-square of 1 means effectively that your fit is sufficient. So that's the.
Okay, thank you.
Yeah. There are, I mean, this is makes assumption on Gaussianities, etc. So there are more in the literature where you can actually go in statistically in high dimension what it means to be consistent. You can also have the model comparison. If it's one model, is it better than the other when the degrees of freedom are different from one model and the other? So this is, yeah, so unfortunately I cannot go in depth into that, but there's a lot of literature and it's an active problem. And specifically if we work on real data, sometimes we not always get down to chi-square equals 1. And then the question is why? Is it because we underestimated the noise? Is it because we need to add more complexity in the model? Where do we need to add complexity? And this is all, not easy questions that we each time have to assess. Yeah. Any other question? Okay, I'm gonna share here this notebook, and I move back to the slides for our last part, where I want to give a bit an outlook. I just put these slides together. Share. Yeah, so here. So here, yeah. Here's some slides that highlight a bit, okay, what can be done in the near future, and then an outlook of what is the promises and ability of strong lenses. So far, I was very technical, the concepts, and put emphasis on this. And in this last part, I want to open up, okay, what are the exciting bits, or what are the things that I'm excited in the next coming years and decade, and why strong lensing may play a significant or major role in certain parts. So one thing is the Hubble constant. It's been mentioned, we discussed it a bit yesterday in terms of the mass sheet degeneracy. And one way to move forward is prioritizing resolved stellar kinematics, but it also requires more lenses. So that's one way to move forward, and we know we find the lenses, and now it's really exciting for me to see when we collect this follow-up data, can we actually resolve the Hubble constant tension either one or the other way? Another an alternative road from the Hubble constant side, but has multiple other application, is lensed supernovae. We expect, in particular with LSST, so the Birrer-Rubin Observatory, to expect like hundreds of lensed supernovae, and a subset of it being of type 1a. Here is an example. I put in introduction slide. Refstal is one that has been discovered. IPTF 16GEU is another one. So these are the only known. Oh, now I think it's a third one that was just published. And these have really advantages. They have a characteristic light curve. The SN supernova fades away, so there's no quasar contamination if you do the spectra. And they have some standardizable magnification. So I talked about, if you don't know the intrinsic source shape or brightness, we cannot really learn much more. So in supernova, we can standardize them. And so we know the brightness they have in the field. And so in the other way. And so we can make predictions of what we can learn actually by using these standardizable features. And so within the next 10 years, we can get down to about the expectations about 1.5% in the Hubble constant, just from this standardizable feature. We can also learn with the standardizable feature about the mass profile of the galaxies. Are there some core density cores in the center? And this may also have implication on dark matter science. So this is kind of like the near-term aspects of this Hubble constant part. And in more broad pictures, currently all the science that has been done on strong lensing has been done on either one lens or something like a dozen or maximally 20 lenses. That's the order that we currently operate when we do this type of analysis, be it on dark matter, be it on the Hubble constant, be it on galaxy density profiles. And so with the upcoming large ground and space-based surveys, this is gonna completely change. We're gonna have tens of thousands of strong gravitational lenses available. Many of them, for example, in Euclid, with space-based imaging. All of them with LSST multi-epoch imaging in multiple bands. So we get a lot of transient phenomena. We can combine data set. So this is really, it's e-folding the number of data we have in hand. And in parallel, what's coming up is extremely large telescopes that allow unprecedented resolution and signal to noise on a subset of systems that we're going to select to do follow-up science. And the same for a James Webb Space Telescope. And for example, on two proposals that got accepted to do science and point that telescope on gravitational lenses to learn about both the early universe, the Hubble constant, and dark matter properties. And one of my current focus now is by making sure we can actually utilize this large sample of lenses. And this also requires moving like forward or do some change in strategy of how we actually analyze the data. And so one thing, you may have been in another workshop or lectures using neural networks or machine learning in broader terms. And that's also something we are exploring and actually image, both in detecting these images, that's very active going on, and also actually doing the modeling and inference, but always making sure is the accuracy guaranteed with this. And that's a challenge and that we are on the way of addressing. And here I just want to highlight two papers if you're more into machine learning, neural networks, but also into strong lensing. You may want to check out these two papers. I think now they're published 2001, and also the GitHub repository where it's basically all open source. The training set was generated with Astronomy, and on top of it, these two PhD students, Sebastian, Karina Wagner, and Jiwon Park, have put in inference pipelines with PyTorch and in doing the hierarchical analysis, just to give a bit an outlook in that sense. Another one more broadly that I'm excited of, strong lensing primarily started as a static probe, but definitely with both with the Zwicky Transient Factory and the upcoming be it LSST and other transient surveys, a lot of basically the statement is any cosmological transient phenomena has a likelihood of being lensed. Well, first of all, every cosmological transient is lensed, but mostly weakly, but sometimes it's strongly lensed and results in multiple images. And another point is that lensing magnifications, in fact, increase the relative chance of detecting the transient when it's strong lensed. So, for example, we haven't talked about gravitational waves, but the sensitivity of LIGO, Virgo, Cagra is increasing. And the sensitivity stops at a certain distance, and that's calculated by how much the actual sensitivity is in terms of the amplitude they can measure. But if an event has a 10 times or 100 times higher amplitude, that is further intrinsic or lensed amplitude, we can reach out to much more volume. And so all this volume is accessible if the phenomena is strongly magnified. And so actually that's an expectation in the community that one of the first higher redshift transients are actually going to be strongly lensed. And it's active search now to see whether there are signals, which of these are strongly lensed. So this is true for gravitational waves. So this is a transient factory, basically. Fermi radio bursts, gamma ray bursts, supernovae I mentioned, and ... So whatever exotic transient there may be. The first ones are most likely to be either strongly lensed or at the high redshift at least. So this is a point, and so there's really a lot of interface between, if you want to do science with these types of transient, you increasingly have to develop an understanding of what is gravitational lensing and how much affects your selection function and the phenomena. That's one comment I have here. And overall, here, it's just a bit of an advertising slide, and I'm going to put it at the end of a colloquium or so. I just also want to stress it here, that gravitational lensing effectively provides a unique window to the dark universe. It's directly sensitive to the overall matter distribution in the universe. It doesn't care what type of matter it is, whether it has luminous components like stars, any exotic or not understood matter components, such as dark matter. It can provide an independent anchor of cosmological distances. This is with time delays. So we can have a clock on Earth ticking, and that absolute time measurement, or the relative time delay with a clock on next to the telescope, basically, and we can measure the scales of the universe. And it's competitive with other cosmological probes. That's both on the time delay as well as in the dark matter, in the substructure, in the small scale cosmological frontier, where our constraints are up there or even now exceeding what the Lyman alpha forest provides. And it's really advancing with increased sample size and improved observational capabilities. So we're still really at the early stages of how we actually can use the phenomena of strong gravitational lensing. The sample size, the quality of data was and just is limited based on how we found them. And that is expected to really open up and evolve over the next decade. So that's quite exciting for me to stay and work in this field. Yeah. So some additional remarks for the end before we can then go in a more broad discussion, but just want to bring that up right now. So this 3-part lecture or course, I know and I'm aware I went very quickly through it, and maybe you are interested in a specific science case that you may or may not be able to utilize or want to learn more about. I want to highlight there are many more notebooks available in the Lenstronomy Extensions notebooks session. If you these are linked, so if you click on the slides, you can link through it. And there are different examples if you want to know more about time delay cosmography, about PSF reconstructions, about another one is actually you can run Lenstronomy turning the lensing effect off, and you can just quote unquote do galaxy morphology analysis like GALFIT, for example. That's being used as well, the code for. You can also look at the Lenstronomy source code and the documentation if certain parts are unclear, and you may perhaps find information also there in terms of the definitions, etc. Then on top of that, there are open source affiliated packages. Two of them I already linked or promote, or three actually of them are here, but there are many more who go into more details and provide almost like end-to-end analysis or specific aspects that they are tailored for doing as either a wrapper or a completely independent package. So there's also a link to a list of those. So it's really getting an ecosystem of related software. And also for those who most want to dig in, you find also some end-to-end analysis. For example, for this paper here is also a link, and also for other papers where you actually see going from the HSD image to actually the constraints we derive. And you may be able to reproduce it or change things that you don't agree and get maybe to a similar or a different result. Who knows? And the last comment is the strong lensing lectures. I mean, I will be updated and provide a selection of additional references. So I will archive the current lecture and put it on the GitHub repo of this summer school, but I hope also to steadily improve the lecture series itself on the repo that is being done. And the last thing, well, no, I leave it here. So the last slide I will then open up at the very end. And I would like now to go into a discussion of what are you interested, what do you think I think, or what you want to know about what promises are, what my opinion is on certain things. Just the floor is all yours in what you want to get out in this last 20 minutes.
Well, I have another kind of silly question is, well, you show us examples about the reconstruction for one galaxy, but when we have a lot of galaxies, a zoo of galaxies, the analysis will be in the same time and n galaxies, or will be one per one and will be like summed up? Who will be?
So, so your question is if you have like hundreds or even thousands of strong gravitational lenses, how you intend or how you envision such an analysis being done?
Yes.
So there are multiple strategies. So one is going in parallel, basically going on one doing the analysis, going to the next doing the analysis, and so on, which you can also feed in parallel to computing clusters, for example.
Yeah, but when they are too close and they're gonna contaminate one another, when do you cut off one and go to the next one?
In terms of strong lenses, so strong lenses are, in that sense, luckily, in other ways, unfortunately, very rare. So there's about 1 in 10,000 objects or galaxies where we say like this is now really a prominent lens. So you have about 2 or 3 gravitational lenses that give Einstein radius within a square arc, between a square degree. And so this is, you don't expect another strong lens just to sit next to it, except if it's in a cluster, in a galaxy cluster where you have a lot of overlapping strong lensing phenomenology going on. But for galaxy scales, they're very well isolated. What we need to take care of is there can be neighboring galaxies. I mean, here you may see just here one, and there are definitely some up here and here down as well. And so what we need to take care is the local environment of the lens. And often it's not sufficient to just, quote unquote, model the main deflector, but we see another galaxies next to it. We also have to take into account this lensing effect. And so this is also part of the work we're actively working on. How is the best way to actually make sure that on a larger window, so to speak, we're actually mapping the lensing effect. And also what I haven't mentioned is it's not just the main deflector sheet that causes lenses. Effectively, lensing occurs all the way on the line of sight from the emission of the photon to the arrival on the detector. So most of it is rather weak, but some of them can also lead to nonlinear distortions. And for example, what we also clearly expect is a lot of small mini halos, so to speak, intervening along the line of sight. And that's actually also a probe we're using to constrain dark matter physics. So how many of these line of sight small halos that may be completely dark, that don't have stellar mass, actually are there, and what are their imprints in our data? And so overall, it's going to be challenging to come up with an analysis that goes through 1,000 or even 100 lenses. And one thing we also have to be always very conscious about is we always make some assumptions when we go in one lens and then we go to the next lens. The question is, what are the covariances there? So how can we treat systematics that may be the same? And so solving one problem and then going to the next and solving, etc., will not be sufficient when we have so high precision signal for this sample. And so we have to come up with techniques that are sufficiently fast that we can redo the analysis basically on the daily or weekly scale to explore systematics or go through for different sets for all the lenses, basically simultaneously. And that's also one reason why we look so much into Bayesian neural networks, because they're so quick. They may not be so precise per lens in extracting all the details in every single pixel. I don't think you can compete really with such a semi-linear forward modeling, but you can compete in terms of speed. It's incredibly fast relative to you running the quote unquote classical likelihood computation. And so definitely at the end, the challenge would be making this decision and waiting between how much you push and how you still trust the analysis. And so practicalities in multiple ways will impact the decisions we're going forward. And there may not be one solution to do it. So there may be a rich variety of how people actually analyze these. And hopefully they come up with similar or consistent answer in the questions we really want to learn about. Does this answer your question?
Yeah, pretty much. And you kind of hinted another one. I don't have an idea, but how much does it? I'm sorry, I don't know if someone else has another question, and I don't want to be this kind of conversation. But how much does it take for a single running?
That's a great question. So the most complex system that I have modeled up, that at that time a PhD student that I worked with modeled, Anna Warshachi, was the lens 0408, and it has multiple lens planes. It was done for time delay cosmography, and we went through several models, and the total cost was something like 500,000 CPU hours, which is a lot. So there is no restriction to, it's very easy to add complexity, and then when you sample it, your dimension explodes in the parameter space, the complexity in the source reconstruction. And so it's getting to a level where, yeah, it's challenging, yeah. The ones that I modeled were something like 50,000 CPU hours, but then, yeah, you go to another lens and it's much more complex and a factor of 10 easily to be added, yeah. Sorry for the background, there is gardening work in front of my apartment. Any other questions?
I have some, but I will prefer the students to make their own first. So who says me? Well, if no others, I can make. So so you already mentioned some of the challenge that is going to be to understand the covariances between the different systems and to study the systematics. But from the theoretical point of view, are there other assumptions that might need to be revisited? Yeah, for example, I'm thinking on the problem that you said that lensing can be caused by substructure all the way along the line of sight, right? And
Yes.
one's usually assume the thin lens assumption for strong lensing, right?
Yes. So from a theoretical point of view, I think that, okay, the thin lens approximation is fine, even if you have multiple planes, you can have multiple thin planes. So that you definitely need multiple of those planes to accurately predict the phenomenology. It's still all very weak gravity. So that is still the case. It's not around a black hole where you really warp the light rays effectively all the way around. So it's very small deflection angles. So I think that is settled enough, but what is really not, so that the two things, so one is really that when we explore different dark matter scenarios, or even in cold dark matter, what is the exact theory predictions that we can say, is this cold dark matter or is this something else? And so we are probing a wide range of halos that somehow gets convoluted in our signal. So we cannot really say exactly what an individual halo is. We cannot really exactly say what redshift it is and what shape it has, for example. And there are different uncertainties that are kind of like nuisances in our analysis but become more and more relevant. One is we don't really understand how many of those get disrupted. Even for CDM, how many of them get disrupted near the main deflector. Along the line of sight, it's a safer game or bet that they basically don't get disrupted. And then also when they're not disrupted, how their concentration is changing and how do baryons impact the shapes. So there are a lot of questions that there's not a 100% clear theory predictions for those. And so there are two ways around. One is increasing the effort of making better theory predictions, say with incredibly high resolution hydrodynamical simulations to test if you trust them, which I'm not so sure, specifically the baryonic parts. The other is identifying these nuisances, such as we don't really know how much the disruption is, etc., and then try to simultaneously constrain these parameters. Obviously, the precision on the target of dark matter dilutes due to it. But when you, for example, have different lenses that are at different redshifts, you have a certain expectation for the differential evolution of what the line of sight contribution is. So just the volume gets more and more the further away your source is. So there's more lensing signal from this. While for the substructure, this is not the case. So this is just in the lens. So there are differential patterns in the signal that we aim to extract. We currently, with like a handful of lenses, we cannot do that. But when we have hundreds of lenses where we know they span a different redshift, they span a different mass range in the halo masses, for example, we can do this checks whether we see in all these dimensions whether our predictions are actually accurate. And it's going to be very interesting for me to see. So currently, the entire cosmological dark matter field, so to speak, be it strong lensing, be it Milky Way, be it Lyman alpha forest, they set basically limits on cold dark matter, basically meaning cold dark matter is consistent with the observations and we can rule out things that are too fluffy. relative to cold dark matter, but they may be sooner or later be the time when this turns and someone comes with a measurement that happens to disagree with cold dark matter. And at that point, it's not just a race for getting better lower or upper bounds, but then it's about looking into, do I really trust that? And if so, what is it? And are there complementary probes? How? And so that's not yet the discussion we have that is so scrutinizing the systematics. It's always easy to just come upper bounds and, you know, CDM is correct. And that's going to be, I hope it's going to be an interesting transition if it happens. Let's put it that way. Yeah, and yeah. So overall, to answer, so the long answer is theory predictions, both for CDM, but then also for alternative theories of gravity is then yet another thing. It's like even warm dark matter, there's a lot of literature, but not as much as for cold dark matter. What is the mass concentration relation of field galaxies at low masses, for example? There's not done so many studies. So even there, uncertainties are, or disruptions with warm dark matter, etc. And then if you go further away, mention like fuzzy dark matter, it's completely uncertain, or, you know, we're struggling even more. And so for us, we are also now thinking of how we can extract more model independent information from the analysis. And then in a second step, ask what models are actually to what shape constrained by it. But it's also it's very interesting and exciting to go this way, but it's also challenging because lensing does not measure one thing at one mass scale. It's a convoluted measurement. And so it's also a bit subtle to do that. So the easiest thing is if we push buttons for predictions for different dark matter models and then see how in agreements the data is, basically. And that push button to see whether things are in agreement doesn't mean we need one model prediction. We need millions of model predictions for random realizations of the same universe, basically. And so we need to rely on semi-analytical description in actually rendering. And what we currently do is try to, at least for cold dark matter, close the gap more between n-body simulations and how we do the semi-analytics. Meaning that we have a scheme where we can do the full line of sight with an n-body simulation, have our validation set, so to speak, and then see whether with our semi-analytic descriptions of the mass functions and of the shapes, we actually can recover CDM that was originally put in the n-body simulation. But even that is a non-trivial thing to do. Smoothing scales of numerical simulations, how they translate into lensing effects. Yeah, there's a lot we dig in that as well. Yeah, so a lot to do on all sides, both observational, data analysis, and theory prediction. Yeah.
Thanks.
Any other?
Someone else?
Ask any question. There's no stupid question. There's only stupid answer that it can give.
Yeah. Well, if not, I have another one. So now from the observational point of view with LSST, for example, what are the thing that the LSST is doing? What are the main challenges you will have with respect to strong lensing? I mean, I know LSST is very big and there are many things to work on there, but so for example, for students and for people that is in the room, if they were joining LSST and interested in lensing, what would you say to put their efforts?
So it depends on, so one challenge we will have is there's so many different science questions you can tackle or use lensing. Lensing is, to first upfront, it's a phenomenon. It's not directly a science question. And so you can use that phenomenon to address multiple science questions, be it H0, be it dark matter, be it galaxy evolution, be it looking at the highest magnified sources in the early universe, or be it just simply a systematics in the analysis of other things. That just lensing is a nuisance that you have to take care of. And so strong gravitational lensing comes in multiple ways. And the more now we have such precise data sets, overall, LSST, Euclid, that there should be less and less a distinction of what is strongly lensed and what is weakly lensed. It's just all lensing. And sometimes you have to understand in tandem this phenomena when you want to go do either one or the other science. So one challenge is to actually talk with different communities because they rely on certain aspects as well. And another challenge, if you, for example, want to do substructure, as LSST will be amazing to design or to learn about or to help you identify or to identify the set of lenses that are most promising you to work on. But it will not allow you directly to give all the constraints without additional data, be it from Euclid, be it from ground-based Keck observatories, be it from HST, Hubble Space Telescope, fingers crossed if it's still flying, that's also uncertain. And so it will be a combination of different data sets. But one thing that will be prominent is also the selection function. So how did you select these lenses? Are these lenses more massive or less massive? Are they all elongated along the line of sight such that they lead to a stronger lensing effect? Or are they randomly orientated? And that's something where LSST is really good at identifying because they have such a rich community of looking at large-scale structure analysis, galaxy clustering, weak lensing analysis. And so there's a lot of excellent data sets available that can help the strong lensing analysis. One challenge will also be, so far we have operated by basically making single queries to access certain postage stamps of a small patch of the sky where we think this is a lens or maybe a lens. And this is going to be increasingly challenging with the data volume of LSST. So how these queries are being done, what type of data products are available, can you piggyback on other data products? Are they good enough for the science that you want to do, or do you need to repackage, reduce parts of the data in the way that you want it? So it's a big endeavor with a large team, and it will require on multiple facets progress. So what I'm most excited about LSST is the transient nature of lensing. And the transient so far is, okay, I mentioned it only for the Hubble constant, but you can also use it for dark matter science because these transients get also magnified and differentially magnified. And this can be due to micro lensing, this can be due to milli lensing, so that the type of substructure we are interested in could be due to primordial black holes or any other like exotic parts. And that will become more and more relevant in actually having a probe. We will be overwhelmed with the amount of data, and it's what is methods that work on this type of data will be a challenge. Yeah, but a lot of exciting and maybe also unexpected outcomes. We may detect the first neutron star merger that happened to be strongly lensed. May happen, and there's a lot of things you can do with that if you have to follow up when you see this being lensed, the gravitational waves being distorted differently, you measure the relative optical magnification, etc. I mean, would be my dream to see this. There's just one is kind of like cranking the standard cosmological probes or questions, and the other is being very curious of what may be the unexpected that you go. And for me, it's a challenge to actually weight those. I think for everyone, but just also keep in mind LSST. It may be that LSST most important science questions that they will do will not be the ones that we anticipate. That happened in the past as well with other surveys in different ways. And it may play around strong lensing as well. Yeah, so it's not really an answer, but just.
No, I think it's a really nice answer. Very inspiring. Thank you.
Yeah. So one last thing I want to do in a minute is my last slide. And that is one that is important for me, is basically your feedback. So this is the first time I run